Hey everybody, in this video we'll be learning how to program neural networks. We'll be covering how we can define neural networks in our program, how we could create data for them, how we can train an AI model, how we can make predictions with that AI model, and how we can save and load our AI models. Now all the coding that we'll be doing is based on the theory that we learned in the previous video, Intro to Deep Learning. So if you haven't watched that, make sure to go watch that now. How this will work is we'll be going over a few programs section by section and seeing how each part is done. The specific programs that we'll be covering are the generic x greater than y program and the x greater than y save and load programs. Essentially, what these programs will do is create an AI model which, given two numbers, can predict which of these two numbers are greater. Now, of course, this could be done much more simply with a conditional if statement. However, for the purpose of learning, this is very good to see how the code is actually written. So let's get into it. Of course, if you want to follow along, you can have the programs open beside you. The code that we'll be covering for most of the video is from the generic x greater than y program. And eventually, I'll say when we switch over to the other programs, the save and load programs. So the first part of the program that we'll be covering is, of course, the libraries. The main library that we'll be using to create our neural networks and train them is PyTorch. Now, there are multiple different libraries you could use for this. TensorFlow is an example of a common one, but the one that, again, we're using is PyTorch. So let's look at the code. The very first line, import torch, imports the main PyTorch library, and it contains all the necessary classes and functions and whatnot that will help us build and train our neural networks. Now, technically, for PyTorch libraries, this is all we need to include. The next couple of lines just allow us to use simple names to refer to specific parts of the library. So we use the name nn to refer to torch.nn, which refers to the nn.Module of the PyTorch library. And this is what we use to actually build our neural networks. nn, as you might have guessed, stands for neural network. We use f to refer to torch.nn.functional, and this will be used to refer to all our nonlinear activation functions and loss functions. And we use the name optim to refer to torch.optim, which refers to our optimizers. Now, of course, this last library that we import is not a PyTorch library. Import random, we're just using the random library to create random training data. So next we'll see how we can actually create our own neural networks. So in the program, this is the section of code which will define our own neural network. And let's go through it line by line. So first, we define our own class, which we'll call net. And this will be the class for our own specific neural network. And you'll see how we'll define its structure. Now, just to note, this class inherits from this nn.Module, which I mentioned earlier. Next, we'll be defining the constructor for the class. And the line below it, super.initialize, just initializes the parent class, which in this case is, again, this nn.Module. You don't need to worry too much about that specific line. It's kind of just necessary syntax that we need. Now, how do we actually define our neural network? How do we define its structure, rather? Well, we could use this linear method. So this linear method comes from the nn.Module. Remember, we just can simply refer to it as nn, in which we defined in an earlier line in the code. And what this method will do is it will define a single layer of perceptrons in our neural network. If you remember from the previous video, the neural networks are just simply made up of layers and layers of neurons, which are all connected together. Now this method takes as parameters how many inputs the layer should have, and it also takes how many neurons the layer should have, which of course is the same number as the number of outputs the layer has. So you could see in our neural network, we define 3 layers. The graph on the right shows visually what our neural network looks like. So in this first layer, we define it as having 2 inputs and 8 neurons. In the second layer, we set it to have 8 inputs and 8 neurons. Remember, the number of inputs must be the same as the number of neurons in the previous layer. And we set our last layer to have 8 inputs and 2 neurons, and meaning that it will also have 2 outputs. Now, let's just talk a little bit more of what the outputs of our neural network will actually mean. Just for this slide, let's call the 2 numbers that we're inputting into our neural network x and y. So we have 2 outputs. The first output will correspond to the probability that the number x is greater or equal to the number y. And the second output corresponds to the probability that y is greater than x. Now, if the first output has the greatest value of the 2, then we can say that the prediction that the model makes is that x is greater or equal to y. However, if the second output has the greatest value of the 2, then we can say that the prediction of the model is y is in fact greater than x. So let's continue. So we just defined what the structure of our neural network is going to be, partially at least. We defined specifically its layers. Now we're going to be defining the forward method. Essentially, what this method will be used for is actually taking our input data and sending it through our neural network and returning the final output. So you can see each of these lines, we pass our input, which we refer to as x. Remember, x will actually be a pair of 2 numbers, and we pass it through each layer. In each of these lines, we also define what nonlinear activation function we want to apply to each of these layers. You can see in the first 2 layers, we apply the rectified linear unit function, and in the last layer, we apply the LogSoftmax function. You can choose whatever functions you like for your neural networks. You just have to choose whatever fits your situation. And then, of course, we return x, which will now be our output. So next we'll see how we can create our own training data. Now, just to specify something, in an actual program, we wouldn't normally do this when we're using neural networks. Instead, we would collect the data from whatever source we could find and write some code which can interpret this data in such a way that it could be passed through our neural network. However, of course, this is again just an educational program, and we'll simply be just creating our own training data, which is randomly made. So this is the function in our code which creates a batch of data, and let's go through it. So first, we have these 2 lists, data input and data output, which will store our randomly generated inputs and outputs. Then we enter a for loop, and here you can see this is where we use our random library. We use this .uniform method, and this will just allow us to generate 2 random numbers from 0 to 10 that we store in x and y, and we store this pair of inputs in this list T. Now, based on these two randomly generated inputs, we'll use a simple conditional statement to determine what our expected output should be. So if y is greater than x, then our expected output will be 1. Otherwise, our expected output will be 0. Now, you might be a little confused since here our expected output contains a single number. However, I said in the neural network, we will have two outputs. Well, basically, what this expected output here is talking about is what do we expect the index to be of the greater value of our two outputs. What do I mean by this? Well, let's say that y is in fact greater than x. From what I said earlier, our neural network then should output a value for our second output that is greater than the first output, right? And the second output will have an index of 1. So here, that's why our expected output is 1. If x is greater or equal to y, then we expect the first output of our neural network to be greater. And the index of that is, in fact, 0. So then we store both the input and output in these two lists that we created earlier. And just to keep in mind, for these two lists, the data in each index corresponds with the index in the other list. So for example, the randomly generated inputs stored in the value for index 0 in our input data list will correspond to the expected value, the expected output, I should say, stored at the value in index 0 in our data output list. And then we'll store all of the data, both the input and the output, in a single list and return that. Now, just to keep in mind, you can see when we generated the data, we did it in a for loop that repeated 8 times. So ultimately, we will have a total of 8 pairs of randomly generated inputs and 8 expected outputs. And this will be a single batch of data. Now, if we want to make an entire set, we have this function here. This is just below the make batch function. Here we have make data, and this will just call our make batch function 100 times, and it will store each batch that is returned by the function in this training data list. And then, of course, it will return the set of training data. So just to see visually what that looks like, you can see each batch, again, will have a set of inputs, which, again, are just pairs of randomly generated numbers. And for each input, there will be a corresponding output, either 0 or 1. And there will be a total of 8 pairs for 8 pairs of inputs for each batch, and 8 outputs for each batch. So now we'll see how we can actually train our neural network to make accurate predictions based off of our training data. So this is the part of the code that will be doing the training. And of course, like before, let's go through it line by line. So everything will be done in a main function. You don't technically have to do this in Python. Here, we create an instance of the net class that we created earlier. Remember, this defines our neural network with the structure that we defined earlier with the 3 layers and whatnot. And whenever we want to refer to our neural network, we'll be using this specific instance, net, with lowercase n. Then we'll use the makeData function from earlier to create our set of training data. Again, we wouldn't normally do this for an actual program. Instead, you would want to collect the data from somewhere and interpret it in a way that makes sense for the neural network. Now next, we're going to be creating our optimizer. So optim refers to torch.optim, which is the part of the library which has all the optimizers. Atom will be the specific optimizer that we'll be using. I mentioned it briefly in the previous video as a very common optimizer that people use. And in the parameters, this first one refers to the weights of our neural network. That's what net.parameters actually refers to. And we also set the initial learning rate. And here we set it to 0.001. So what the optimizer will actually do in the context of the code is it will, of course, adjust our learning rate in a way that's optimal. We talked about how having an adaptive learning rate is more efficient for deep learning in the previous video. And it is also what will actually modify the weights of our neural network. That's why we pass them in as a parameter. We're telling the optimizer what weights it needs to modify. Here we have the main training loop. You see, first we actually define this variable epochs, and this is the name that we commonly use in any deep learning code, and it simply defines the amount of times that we iterate through our training data. You could see here that we have it set to 30, so we'll go through our entire training data set 30 times. In each iteration, we'll also go through each individual batch and pass each individual batch through our neural network. So in this first part of the loop, this is just managing the data. So we first break down our batch into the set of inputs and outputs. We then store the values of our inputs and outputs in tensors. Now, tensors are the primary data structure that libraries such as PyTorch use for storing and working with data. Now, for the purposes of this video, you could just think of tensors like lists or arrays with n dimensions. Essentially, though, all you need to know is that we're storing the inputs here in this tensor training input or tensor tin, if you will, and the outputs in this other tensor training out. Now the next few lines of code, this is where the actual training is done. So first, we reset the gradients of our neural network to 0. In the previous video, we talked about what gradients are and what gradient descent is. We then pass our input data through the neural network and get the predicted outputs from that. So you could see we use the instance of our net class, and we pass the input as a parameter for it. Then next, we calculate the loss. And you can see we have a loss function, and we have as the parameters the predicted output from our neural network, and we have as well the expected output from our training data. Now, the specific loss function that we use, this is again from our PyTorch library. We're using the negative log likelihood loss function. You could use whatever loss function is, of course, best for your scenario. Then in this next line, the backward method is actually what we use to perform backpropagation, and this calculates the gradients for the weights of our neural network. And then in this final line, we use the step method, and our optimizer will adjust the weights of our neural network based on the gradients, of course, to lower the loss. So in the previous video, I talked about the process of gradient descent and the math behind it, but luckily enough, the libraries actually take care of all the math for us. You can see here that we could do the process quite simply with just a couple lines of code. So of course we would apply this process to the data in all of our batches in the entire training data set. And we do this many times until eventually our model has been trained. And then with that, we should be able to make accurate predictions with new testing data. So here's the code. We have it set up to make a single prediction based off of a pair of inputs that the user gives. So the first line just simply reads two numbers from the user that we store as x and y. We then store those inputs in a tensor. Remember, tensors are the primary data structure that PyTorch and similar libraries use to store data. And we make the tensor in such a way that it's suitable to be passed into our neural network. In actuality, the tensor that we used earlier for our training data had 2 dimensions. So here we're just adding an extra dimension to match the same structure of the one from earlier. You don't have to worry about this too much. This is just how we have to pass our data into our neural network. Then here we do just that. We pass the data into the neural network and we get our prediction. Now, just to clarify, because I don't believe I actually said it earlier, here when we do this, when we pass the data into this instance of our net class, the forward function from our net class is actually automatically called. And remember, this is what's actually taking our input data and passing it through each individual layer, applying all of the necessary nonlinear activation functions. So then now with the output, we can apply this argmax function to it. And what this will do is it will simply return the index of the output with the greatest value. And then based on that index, we can determine which of the 2 following cases our AI model has predicted. So as you remember from earlier, you should remember from earlier, if the index is 1, then we expect that our input number y is greater than x. If our index is 0, then we should expect that x is greater or equal to y. So now we pretty much covered all of the elements in the generic x greater than y program. However, in an actual setting, we normally wouldn't just want to create and train a model and have it make a couple of predictions and be completely done with that model. Instead, if we wanted to make an AI model that we're actually using in the future, we would want to create it, train it, and then save it in some way to be used for future applications. So now we'll see in these next couple of programs how we can save our trained models and load them in new programs to be used for, again, other applications. So this first program, this is where we'll be training our model and then saving it. So you'll see most of it is the code that we covered earlier. We have the definition of our very own neural network class with the structure that we defined. Here we also would be creating our data, or in actual setting, we'd probably be collecting it and interpreting it. And then, of course, we also have the training loop. Again, this is all the same code that we pretty much covered earlier, except we have this extra line. Here, this is the line that allows us to save our trained model to whatever specified file we want. What we mean by saving the model, what we're actually doing is we're just saving, again, a set of weights. And then now, in the second program, we can load the model, which, again, has already been trained. We don't have to train it again, and we can use it to make a prediction. So a lot of it, again, is the same code. We still, this is important, we still need to have the code which defines our own neural network class and its structure. And then the rest of the code is just the code for making a prediction, where we call our own neural network. However, we have, again, an extra line, and this is the line of code which will allow us to load our already trained model from the file that we saved it to earlier. So now, let's just summarize everything that we covered in this video. So, in the context of these x greater than y programs, which in these programs just created a AI model which, given two inputs, could predict which of these two inputs are greater. In this program, we learned all the necessary libraries that are needed to create your own neural networks. We specifically covered the PyTorch library. We saw how we could create our own neural network. Again, we used this nn module, and we saw how we could define the layers of our neural network, as well as how our input should pass through those layers, and how we could define our own nonlinear activation functions for the layers. Then we covered how to handle our training data. For our specific case, we actually created our own training data. Then we saw how we could train the model, again using pretty much the same steps of training that we mentioned from a theory perspective in the previous video. We then just now saw how we could save our model in a file for later use and then load that file in a new program. And then finally, we covered how we can make predictions with new data with a trained model. And that would be the end of the video. Thank you all for watching.